Okay, everyone, welcome. Let's get started. So we're going to have a brief first look at something called residuality theory. How many of you were in my workshop on Monday? You came back. You're going to hear the same thing, but really, really fast this time. Okay, so a little bit about me. I'm the founder of a company called Tulip Technology, based here in Stockholm, former chief architect at Microsoft, former global lead for solution architects at Microsoft. And everything that you're going to see here today comes from projects I did in that time where we were trying to answer the question, what is an architect, what do architects do, and how do we make architects faster? And in order to do that, we have to do some pretty radical things. Today's talk is a summary of this paper, which was officially released last Friday, which is some fairly heavy stuff. So the problem that we're trying to solve, we were asking ourselves, why do some architects succeed? Why can some architects go into insanely complex engagements where nothing is nailed down, where none of the stakeholders know what's happening in the environment and still deliver, even in conditions of high uncertainty? And the problem that we're trying to solve is that what we do as architects, as software engineers, is we design software structures. And software structures are mechanical things. Okay? They're not particularly complex, they're complicated. They're ordered, they're structured, they're testable. And that's what most of our school life focuses on in terms of if you've done a degree in a STEM subject. It's this ordered, structured, logical way of thinking. How do we build this software? How do we test it? How do we get it to do what we want? And what we do in the real world is we take this ordered, structured, simple, innocent piece of software and we put it into an unstructured, dynamic, constantly evolving, constantly changing environment, which has people and businesses and society and economics and politics and all of those things all moving around all at the same time. And as soon as we build our little bit of software and put it into this environment, things start popping up in that environment, like this X, which is a point, a state in this environment, which we weren't prepared for, which we didn't understand could even exist or could even pop up. And quite a number of these things pop up, and this isn't a new story for any of you who've worked in software engineering. As soon as we start working with the code, the environment starts to change. We get new ideas. And these things, these X's that we can't see or predict or control, we call stressors, because as soon as they erupt, as soon as they emerge, they start to stress the system. And the way that we cope with this is that we kind of give up. This environment is too big, it's too scary, too dynamic, too unpredictable. None of the tools we learn in our degrees can help us with this. So what we do is we shrink this bubble. We make it smaller, we make it easier to manage. And we use tools, well-meaning tools, things like requirements engineering, and we force stakeholders to be really precise. And if they're not precise, we ignore them. And we use things like risk management. And then we make things up and say, well, this has a very low probability of happening, so I'll ignore it. Or this has a very low impact, I believe, so we ignore that too. And we reduce the area of the system so that we can more accurately point out these X's. And as soon as we do that and put this thing into production, another X, this red one, pops up. And we're back in the same situation, and this happens constantly. And this is the problem with software architecture. How do we design structures for a bunch of X's that are going to pop up all the time when we don't know what they are, we don't know where they come from, and we don't know how they're going to impact us? And like I said, some architects, a good number of architects, a good number of software engineers are able to do this. And the answer to why they're able to do this is in this book, which is called The Reflective Practitioner by Donald Shun. It was written in 1981. And it talks about how most professionals in complex environments develop something called reflective practice, where we're able to use a gut feeling to make decisions that are more or less correct. But we are slaves to an idea called technical rationality, which tells us, based on our educations, based on our cultural and philosophical beliefs, that we should be working in a structured, analytic way to figure out these problems. There should be a formula where we just go and put in some values and figure out the answer. And so gut feeling is never really accepted. And so how do we solve this problem? How do we create more architects? How do we get them to have this gut feeling faster? Well, we have to be able to describe what is this gut feeling? What is it that senior engineers and architects are able to do? The way that we make architects today is that we throw them in at the deep end and we come back in 5 years, and if they haven't drowned, then you're an architect. We need a better way to do this. And once we start investigating this problem, we very quickly realize that what we're dealing with is the problem of uncertainty and complexity. And some people are very, very comfortable with uncertainty and can work with it. And some people don't like it at all. And there's an awful lot being written and an awful lot being said about the subject of complexity science, which is an area which I research in. And quite a lot of it is kind of useless for us as software engineers. There's a lot of very big words and fancy ideas and things like that, but it never actually gets to the point of saying this is how you design a system. So what we're going to do is we're going to take a select number of ideas from the complexity sciences and look at software engineering from that perspective. The first thing we're going to talk about is the concept of random simulation. So if we have a circle inside a square, and the square has a side of length x, what is the area of the circle? How do we figure that out? What we do is we just get some darts and we throw them at it. And we throw the first dart at it, we throw the second dart at it, and we say one dart hit the circle and one dart didn't. Therefore, 50% of the area is probably covered by the circle. And then we say, so the area of the circle is x squared over 2. That's a very small sample, a very dangerous guess. But as we add more and more points to this, we get a more accurate reading of the area of the circle, and this is testable in quite a standard experiment. And when we do things like requirements engineering and risk management and gather information and sense making, or whatever it is we call it these days in our enterprise environments, and we're building software, this is what we're doing. We're randomly simulating the environment. When we talk to stakeholders and say, tell me about your requirements, what we're saying is, tell me about the future of this dynamic, ever-changing, unpredictable system. Nobody can actually do that. So what we're doing is we're bullying our stakeholders, and what we're saying is, tell me about a future you can't possibly know about, and then I'll build a system, and when what you've told me turns out to be wrong, I'll charge you again for doing exactly the same thing, which is a fantastic business model. But they're on to us. So random simulation is a way to get out of uncertainty. And when we do requirements engineering, when we do risk management, we're actually doing random simulation. But we've convinced ourselves, if you read a book about requirements engineering or a book about risk management, that we're actually doing something really thoughtful and analytical and logical. But we're not. If we threw darts at a dartboard, the results would be fairly similar. That offends some people. Another really important concept from the complexity sciences, which is relevant to us, is something called a Kauffman network, which was developed by a biologist and a complexicist called Stuart Kauffman in 1969. And a Kauffman network is a Boolean network. And so every node in this network has two states, 1 or 0, on or off. So it's really helpful to think about this as light bulbs. They're either on or they're off. And if you have a Kauffman network with a certain number of nodes, say n is the number of nodes, then this random Boolean network, so these things randomly switch on and off based on a little function inside each of them, the number of states that this system can arrive in is 2 to the power of n. And Kauffman ran these experiments with a computer model where n was 100,000. So 2 to the power of 100,000 is an absolutely enormous number of states that this system can arrive in. It's huge. And Kauffman discovered something. If he put links between the nodes so that they were dependent on each other, so that the output of one node's function fed into another, and the next node made its decision based on the input from that node, in this way connecting the thing, the number of states fell, and it fell massively from 2 to the power of n to root n. So for his system with 100,000 nodes, the number of possible states fell from 2 to the power of 100,000 to the square root of 100,000, which is 317. And this is a fundamental finding in the complexity sciences. This is how we survive in a world where there are millions of things all moving at the same time. They constrain and restrict each other, and they reduce the number of possible states. And that's the only way, as human beings, that we could ever navigate something as complex as a city or a forest. Because the number of states in the possible state space is really, really restricted by the interaction of the elements. And each of these 317 states Kauffman called an attractor. And when this first happened, when he ran his simulation, he thought this was really weird, because every time he ran it, the system just kept returning to the same 317 states all the time, which is really strange. And so we call these things attractors. The system seems to have some sort of attraction to this particular state. This is going to be really important for us. And he talked about something then called an NKP analysis. And if you take your network, it looks like this. The first thing we can say about this network is that n equals 12. Now, as software engineers, when we're designing our systems, we want to keep n low, right? We don't want it to be 1. We know that's bad. It's called a monolith. But we want to keep n low. We don't want thousands of microservices. Well, not anymore. Some of us tried that. But we don't want thousands of microservices. We try to keep n as low as possible. We have another value called k, which is really important in this network. K is found by finding the node in the network that has the most connections and counting the connections. In this case, k is equal to 3. So Kauffman discovered that when k is equal to 2, everything's nice and ordered and stable. The same attractors are visited all the time, and the system arrives at its attractors very, very quickly. And the third thing is P, and P is bias. And bias means that we take the function in one of these nodes and we give it a much higher probability of returning a certain result than any of the other results that it will return. And so we bias it towards either 1 or 0 in a Boolean network. In software engineering, we bias our components, our nodes, by using things like schema, contract, validation, error handling, flow control. All we're doing is putting bias on the component so that it does a roughly similar thing all the time. And so when we look at software engineering and architecture and the uncertainty in an enterprise environment, we can actually describe all software engineering as a 2-step algorithm. And this applies to every software engineering methodology you've ever been taught or ever thought about or ever used. The first step is a random simulation of the environment. And this is a hard pill for some people to swallow who think that they've been working in a very logical and ordered way, especially if their job is a requirements engineer or a business analyst. The second step is an NKP analysis of your component structure, where you're trying to keep n low, you're trying to keep k low, and you're trying to raise p as much as possible in order to keep order in the software system. You can go and get any book that describes how to design and how to think about software, any methodology, any description, any tutorial, any class, and you'll find these two things at the root of what we do. So this can be used as a general description, a general theory of software engineering. And the thing that makes it reflective, the reason that it's reflective is because we don't know we're doing this. We don't know that we're doing random simulations, so we don't realize that the best architects are doing really random simulations. and we don't know that we're doing NKP analysis. We think we're doing microservices, or we think we're doing Grasp, or we think we're doing Gang of 4 or something. So we don't talk explicitly about NKP analysis because we're trapped in this technical rationality, this idea that things should be analytical and structured. And it stops us from seeing what it is that we're actually doing. Residuality theory then, which we're going to look at now, talks about how we can make the random simulation more random, which is something we need to do, and make the NKP analysis explicit. And to understand that, we need to look at another little concept, and that is the concept of an attractor network. So when we take our innocent, mechanical little piece of software, which we love and adore, and put it into this dangerous, dynamic, constantly changing, unpredictable environment, we have this massive bubble with all these different states that the system can arrive in. But we know now that those states aren't all going to happen. We know that a number of attractors are going to exist, and the system's going to constantly arrive back at those attractors all the time. So the problem space is actually much, much smaller than what we thought it is, now that we've looked at Kauffman and understood how complex systems actually work. And what these are is a network of attractors, and we call this an attractor network, and the system moves between these things all the time. And the thing that makes it shift is still X's. Unexpected events in the business environment pushes the system from one attractor to another. And as we move around this network and push from one attractor to another, our architecture either continues to work or it falls over completely. It has to be rebuilt, or we have to pull bits away, we have to change it, we have to change the structure of it. And so good architects with a lot of experience tend to build software systems that respond to a lot of different attractors. Junior architects, junior developers tend to build systems that respond to one happy path attractor, which they learned about when they said, "Tell me your requirements." And so we come to the concept of a residue. They say that every problem in computer science can be solved by adding another layer of indirection, and that's exactly what a residue is. The residue is how we capture this idea of an attractor in our architectures. And so we start our design by, first of all, finding out about this happy path attractor. Tell me your requirements. What is it we're trying to do? Are we trying to sell bicycles? Are we trying to sell books? Are we trying to sell hedge funds? What is it we do? And for that attractor, we develop an architecture. And we call that the naive architecture, because we haven't explored very much. So we call it the naive architecture, or as some people like to call it, production. And then what we do is we think about a form of stress. What could potentially pop up in this environment? What could happen in this environment? This is our random simulation. And we come upon a new attractor, and that stressor could be something like a competitor drops their price, or the market changes its mind about our product, something on the business level. And what we do is we build another architecture. We change our naive architecture so that it survives this particular attractor as well. And that new architecture that we create, we call it a residue. And residue just means whatever's left over when stuff falls apart. And we do this many times. We come up with these stressors, and we come up with new residues, and eventually we build up a whole bunch of residues that describe an architecture that can survive many, many different attractors within this network. And what we're doing is we're leveraging a couple of things. We're leveraging the mathematics of networks and the mathematics of attractors, and we're leveraging probability. So one residue, what we usually find, one residue will survive way more than one attractor. One residue will survive actually a whole bunch of different attractors. And each attractor can be triggered in the business environment by a whole bunch of different X's. So a whole bunch of different stressful things that we could never have predicted, never have controlled, never understood, will push the system to one of these attractors. And when one of these X's happens, then it'll push the system to one of these 4 attractors, which will be survived by this residue. And so we'll have an architecture that actually continues to work. And the good news about this is that we only need to identify one of these X's to identify one of these attractors, to identify the residue that's necessary to survive all of them. And so we're leveraging the probability, we're leveraging the properties of networks, and we're saying this is actually quite easy, right, when we think about it like this. So why don't we just do this all the time? Why doesn't this work? Well, you know that between 67% and 83% of IT projects fail. This is probably the reason why the other 33% actually succeed. We don't have to know everything. We don't have to gather everything in an environment in order to be able to build something that survives. Another problem is this. It's called the curse of high dimensionality. And this is what happens when people try to be random, because we can't. And when we try to do a random simulation of the environment, and we're encouraged by these tools like requirements engineering and risk management and design patterns and all these things that we've been taught are good, we tend to focus on what we think is probable, which gives us a really skewed picture of how big this circle is, because we focus on the same things over and over and over again, and they're all related to each other. We're not random enough, so we don't catch enough of these X's. And so what do? We have to introduce a certain level of silliness and playfulness to break these patterns. And so one of the things I like to teach my students to do is to use their first stressor should be lizards. Giant fire-breathing lizards emerge from the Baltic and destroy Stockholm. Does your architecture survive? And this seems silly, right? We don't tell management about these things, okay? We do this in our own little room with the door closed. This seems silly, but if I have an architecture that survives this lizard, I have an architecture that survives social unrest. I have an architecture that survives a pandemic when there's no one on the streets of Stockholm. I have an architecture that survives a power outage. I have an architecture that survives a war, an architecture that survives an invasion, an architecture that survives a major cyber attack on Stockholm. And so with this one silly little irrelevant nonsense X with a probability very close to zero, you can never say zero in complexity, the lizards might be there. With a probability very close to zero, gives me protection against a whole bunch of other stuff that I'm not going to be able to predict or control or maybe even think about or see in these complex social systems. So what we end up with is this thing called a residual architecture, and we have our naive architecture, and then we have all of these residues that are built on top of it using different forms of stress. And all of these architectures, this is a set of architectures, are very, very related to each other. They have a lot of overlap, they have a lot in common, they're very, very interconnected. They are, in fact, a network, which brings us back to familiar territory. And what we have to do now is boil these back down into a coherent architecture, because we don't want to build this many separate things. But what we've actually done is we've changed the way we do architecture. Before we looked at this kind of way of doing things, what we did was we looked at a problem and we started breaking it down into processes and components straight away. But now we're breaking it down into residues, which are a completely different thing, completely different way of thinking about the problem. So it requires a bit of thinking to really get this stuff. And so the process that we're doing is called residual analysis. And it's got two steps. One is stressor analysis, and the other, which is a random simulation, and the other is contagion analysis, where we don't want stress to spread through our residues and destroy the whole architecture. We want to compress them, but preserve their ability to meet different attractors. And what we're actually doing is we're using stress to drive our design decisions. We're moving away from requirements, we're moving away from risk management, we're moving away from ideas of probability, because we were never able to talk about probability in these kinds of environments. And you can find these ideas, the roots of these ideas I found in a book called Anti-Fragile by Nassim Taleb, which I bought in an airport many years ago. I'll give you an example of how this works in real life. So this is semi-fictitious, based on a number of different projects. None of them were Tesla. Building a network of fast charging stations for electric cars. The naive architecture was like this. You would drive up to the car charger, hold up a key fob, a message would go up to the cloud, it would recognize who you were, see if you'd paid your subscription and let you charge your car. That was the naive architecture, which was the one that was put in production. And so what we do is we run this stressor analysis on it, and this is the cleaned up stressor analysis. This is all politically correct. We take the lizards out and all that stuff. We can show this to management. What we do is we notice a pattern here. The third stressor is what happens when the login fails. When the login fails, you've got a rich, angry customer with a half ton of metal in front of a car charger. They're not going anywhere because they're not charged. There's going to be a queue behind them. This is massively irritating. It turns out to be a huge problem in the naive architecture because these key fobs are very sensitive to magnets and rain and cold and all of those things. So we have to change. We have to build a new residue. Our first residue has to be a little bit different. And we add some technology, automatic license plate recognition. So we scan the license plate, we let anyone charge, and then we send them an invoice later on. The cost of letting a stranger, someone who isn't in the network, charge and then sending them an invoice is actually very small compared to the issues of having to deal with key fobs. The next stressor that's interesting is number 8. If someone accidentally damages a charging station or criminal or vandalizes it or drives into it, both of those things are going to happen. We need some redundancy there, extra chargers, and we need some security cameras. Number 12 is very interesting because it happens a lot. Customers would turn up, plug in their electric car, and go and play golf. And they could be away for 8 hours. And that's 8 hours where our asset is locked, because when you plug in an electric car, only the owner of the car can pull it out. We solve this problem by using ALPR to recognize the license plate and by invoicing per minute on a sliding scale. So if you stay beyond the 25 minutes of a standard fast charge, it starts to cost an incredible amount of money. That discourages people. It also means we get paid more when this happens. And getting paid more is generally considered to be a good thing in business. So far, so ordinary, okay? This is normal business analysis, normal risk management. The interesting thing in this analysis is stressor number 14 down here, something called icing. Icing started happening in the United States, where it was assumed that owning an electric car was a political statement. And things have been getting a little bit agitated there. And what happened is people with ICE vehicles, so internal combustion engines, started parking their cars in front of their diesel or fossil fuel driven cars in front of electric car chargers, just to annoy people who had electric cars, just to make life a little bit more difficult for people who had a different political opinion. This was not something we considered. It's one of those things that's really, really difficult to look into the future and see this kind of thing happening. But if you combine the residues for stressor 12 with invoice per minute, stressor 8 with security cameras, and stressor 3 with automatic license plate recognition, this was never a problem for us. We already solved it. And this pattern is one you see over and over and over again when you're using residues, is that eventually when you stress the system enough, it starts surviving things on its own without needing any help. And we see this behavior in biological systems, we see it in economic systems. We don't generally see it in technological systems or software systems as yet. The reason this is happening is that we identified 1 or 2 X's that played to the right attractors when we built the residues, and we had residues that served those attractors in the network, and the problem is solved. And we see this happening all the time. And as you continue through this stressor list, you get to a point where it's almost impossible to stress the system, no matter how silly or how ridiculous you are. And the sillier you are, the more ridiculous you are in gathering these stressors, the more random your simulation becomes, the more attractors you discover, the more stability you find. When I present these ideas back to senior architects, they say, yes, this is what we're doing most of the time. But we don't have any way to externalize it. We don't have any way to describe it. We don't have a language. Because when we describe it in the way that we actually do it, which is a creative act, it sounds silly. So we just tell people to read about design patterns when a junior architect asks, how can I learn this? You might think that that was a uniquely American problem, but it's also come to Europe. And this comes from Munich, where someone started stuffing, for the same reasons, they assume there's a connection between electric car ownership and vegetarianism. So we're going to stuff mincemeat into the electric chargers. Nobody had a risk management chart with a probability higher than 0 that someone was going to stuff raw minced meat into these things. Risk management will never catch these things. Residuality is the only chance to be able to do this. And so residuality theory then says that hyperliminal systems, which we'll come to in a minute, can't be modeled as processes or components. We have to model these systems as a set of residues in order to be able to survive this huge amount of unknown stressors. And these systems are described as a stack of residues. And a residue is just a fuzzy view of the system under a particular form of stress. Generally, it consists of people, information flows, infrastructure, and software functions. But that's not that important. The next thing we have to do is pull all these residues together into coherent architecture and not screw it up. Because at the end of the day, we still have to have a list of components and functions, right? We still have to make those decisions as architects. And we'll have to make one further definition before we do that, and that is the idea of a hyperliminal system. So some systems are ordered, I've already mentioned. Software is ordered, it's predictable, it's structured, it's logical, it's a machine. If you write some software, put it on some reliable hardware and leave it in the forest for 1,000 years and come back to it, it will still be running the same way. It won't have gone through an emo phase or changed its mind about the universe or anything like that. It'll just keep running. Some systems are disordered, they're very loosely constrained, they're unpredictable. People, businesses, society, politics, economic and biological systems. The systems that have the ability to survive unknown stressors tend to be disordered. And so we describe the kind of system that we have to build, that we are tasked with building as architects, as a hyperliminal system. That is a structured, ordered core and a disordered, disorganized, unpredictable environment. And they call it hyperliminal because liminal means a space between two things, because as an architect, you've got to constantly move between this structured, ordered world, which we all have a really good education in, and this disordered, weird, unpredictable, uncontrollable world, which we have no education in. They didn't tell us about this at school. That's why we're so confused and angry all the time. So we have to think about how do we break a system down into components. And in 1972, a guy called David Parnas talked about how university students and new graduates break systems down into components. And it's the same in 2022. If you give them a process which goes A, B, C, D, they will give you components A, B, C, D. This is dangerous because if something gets shaky or changes or hurt in component B, it affects A and C and the whole process slows down. And you have to recode everything. They do the same thing for D, E, F, and G, and because our ancestors are mathematicians, we get extra points for elegance. We'll wrap all these things together, and we'll say A and D are kind of similar, and B and E are kind of similar, so let's put them all in one component and call it a framework. What happens then is, when a stressor hits component E, it spreads to B, it spreads up here to A and D, here to C and F, and the entire system gets taken out. And Parnas said this isn't a very smart way to build systems, but it's kind of standard. So what we do instead, Parnas called non-conventional decomposition. And in non-conventional decomposition, you try to figure out what's going to change, and you build your system around what's going to change in the environment, which sounds really sensible and really smart. And we all know how to do this, right? No one hard codes database strings, database connection strings anymore. Almost no one. But there's a problem with this. We don't know what's going to change. And what happens is something pops up in the environment, an X, a stressor that we haven't thought about, and it hits two of these components. It hits G and it hits C. And G and C are, from our architectural perspective, from our functional perspective, they're not coupled, right? They're far away from each other. In network science, if you have three nodes, A, B, and C, and A is connected to B, and A is connected to C, that implies an implicit connection between B and C. They are coupled. C and G are coupled by this stressor. And this kind of thing is hard for us to talk about because there's no functional connection. This is actually a non-functional coupling. It's a non-functional requirement. And we, as an industry, make a real mess of these things all the time. And it turns out that there are lots and lots and lots of examples of this coupling, and you find them as you go through your stressor analysis. As you stress and shake the system and move it to different attractors, you'll find this hyperliminal coupling between components which, when you look at the architecture diagram, have no suggested coupling between them. And this spider web, then, of invisible connections actually represents an accurate and real-world picture of the non-functional requirements, much better than going to our poor business stakeholders and saying, tell me your non-functional requirements, when they have no idea what any of those words mean. So then we do our contagion analysis, and contagion analysis is based on these Kauffman networks. It's based on N, K, and P. We want to get N down, we want to get K down, and we want to get P up. How do we do that? The way that we analyze networks is by using matrices. And the first thing we do is we use adjacency matrices to find out what's dependent on what else. And we break our system down into information flows, flows of information between people and components. And then we look for patterns. And for example, a pattern that we see a lot is this, where we have these nice little neat triangles with no reflection across this. So there's no interdependency. And that means you have a nice, simple, ordered process. You can give this to a junior developer without panicking. Sometimes we'll see reflection across this middle line in the adjacency matrix. And this means that we have components that are interdependent. We don't like that. That causes us headaches and problems. It can also suggest feedback loops. It can also suggest that we're trying to solve more than one process with the same model. Sometimes when you see a lot of this reflection, it reflects a very complex environment or a business analyst that doesn't really know what's going on. And sometimes it goes completely out of control. And this represents, customer service at a mobile telephone company. When you call them up and say, I want to change from a business to a personal account, anything can happen. Any step can jump to any other step. There's no real control. The process is fluid. It changes every day. The people who are answering the phone aren't particularly well trained. This is a Markov process. And so with these simple adjacency matrices, we get an idea of what's dependent on what else, what kind of situation are we working in here. And then we use something which really opens this up, something called an incidence matrix. And we go back to our stressors and we apply them to either components or flows or functions within our architecture. And this gives us a whole lot to think about. So we put all our stressors here as rows and all our flows in the architecture as columns. And we put a 0 if the stressor doesn't hit that flow, and we put a 1 if the stressor does hit it. And then we go and we take some totals. And we can see here, where we have a 5, that this is one of the most dangerous stressors to us. And that means we need to take care of this now. And we also have totals here. And we can see that this particular flow is very susceptible to stress. It gets hit all the time. That means we've got to protect this guy. We've got to have extra, we've got to have redundancy, maybe diversity. We've got to have really good error management. Another thing we see is that any stressor that has more than one thing that it hits, that's an example of hyperliminal coupling. These two things are coupled. And if we go back to our adjacency matrices and see that they're not dependent on each other, then we know that we found non-functional requirements. And out of these matrices, we get a really good picture of our non-functional requirements. Another thing that comes out of this is that we can see that certain flows and certain components have the same pattern of response to stress. When something has the same pattern of response to stress, it means it can live in the same component. And suddenly we have component boundaries that are emerging out of these matrices. It's not gut feeling. It's not a design pattern we read about. We're not copying something else. It's an actual structured way of deciding where are the boundaries in this application. And this leads to very, very resilient architectures. Once we're done with that, we still have to go back and do classical systems engineering. Things like failure mode effects analysis, DevOps tools, ATAM, if you have the architecture trade-off analysis method, testing strategies, all of these things, all of them are actually focused on NKP values. And the final thing we can do, once we have our architecture, is we can ask ourselves, have we done anything useful at work? Not something that us architects tend to actually spend a lot of time on. And what we do is, we take our naive architecture, which we started with, and we take our list of stressors, but at the start of our project, after we've got our list of stressors, we hide half of them. We take them away and we put them in a drawer. We're stealing a trick from machine learning. So the first set of stressors is our training set. And we use that to create this residual architecture. And we do our contagion analysis and we boil it down and we get a set of components and we get a structure. And then we take our second set of stressors, our red stressors, which we haven't looked at yet. Now, for both the naive architecture and the residual architecture, these stressors are things they haven't been exposed to. They are unknown unknowns. They have not been designed to cope with these stressors. And we take each stressor one at a time and we run it over the naive architecture and we say, will the naive architecture survive this stressor? If it survives, we increment the number x by 1. If it doesn't survive, we don't increment x. We do the same thing for the residual architecture. We get the number y, and if the residual architecture survives, then it gets a 1. If it doesn't survive, it gets a 0. If both get 0, the architecture that is best placed to survive, that is cheapest to fix, cheapest to move to the next point, gets the 1. And if y is greater than x, then we as architects have demonstrably built a system that's more likely to survive unknown sources of stress than the naive architecture. And this is called a binomial sign test, and it's used to establish statistical significance. And so my research is running a whole bunch of projects through this process and showing that this happens often enough to be useful to do in every single case, which will make it a scientifically verified approach to software architecture, which will make it kind of different than all the other stuff that's out there. And so, what happens is we arrive at a solid design, which survives known stress, obviously, survives unknown stress, which is real resilience. It will have all the required functionality. You'll capture all of that functionality as you talk about flows, as you stress the system, as you look at attractors. You don't need to ask about functional requirements. And another byproduct of this is that you very quickly expose holes in the business thinking, such that, like the idea with key fobs, which was obviously on a business level, wrong. What we haven't done is we haven't done any requirements engineering. And we haven't made any impossible predictions about the future. We haven't tried to predict exactly what's going to happen in this environment. We've just made sure that we've explored enough of the attractors in the attractor network. We haven't done any of this old school linear risk management where we make numbers up and say this has a probability of 37% and an impact of $100,000. Because that's pointless. And we have avoided missing non-functionals. And so this is essentially a new theory of software engineering, a new way of doing things, a new way of thinking about things. It replaces all those old architectural frameworks. Things like TOGAF and enterprise architecture methods, we don't need those anymore if we're doing this. That upsets people when I say that. This is also a really, really good way to train architects. If you take junior architects or senior developers who haven't done architecture so much and they're stepping up, this will allow them to practice and become architects much, much faster than the old school ways of just letting them draw in or sending them on a TOGAF course. It's also really tough. You have to think really critically. You have to think about your own bias. You have to think about your own impact on architectures and where bias is expressed. There's a whole bunch of articles that I've written on this. These two are a little bit softer, written in an enterprise architecture magazine in the United States. There's a bunch of computer science papers and even one philosophy paper, because there's a philosophical aspect to this that asks, Why do we believe what we believe as software engineers? Where do we get those ideas from? There's links to all those articles in the slides. And here you have my contact information if anyone wants to reach out and ask any questions. And we have 5 minutes left, which means I made it to 1 minute a slide, which is pretty cool for me. Any questions? Sorry, as? Yeah, a network, yeah. I'm processing. There is a network of residuals, and then the way that we analyze the network is through using the matrices. And that means that we're considering the network. I don't follow purely mathematical methods for handling graphs and networks, because I think what I found was that when I did that, I lost software engineers, so I just made it much, much more practical. So sometimes we jump several steps at once, just because it fits in the head of a software engineer or an architect who maybe doesn't have a background in graphs or networks. Any other questions? Oh.
The matrix you had?
Yeah.
Where you and then with X, where you see this residual affected this and this. Is that the practice and theoretical in your head? You see that this problem affects this, or are there some tests or tools you can run to see what problem affects what functions?
Yeah, it's mostly it's in your head when you first do it. It's a future research direction. Can we write algorithms that speed this up for us? But that's not going to be done this year. But the tendency is there. Everyone who looks at this says, hold on, we could build tools that will do this for us, and that's exciting. But we have to learn how to do this well first before we build tools to help us, and we have to show that it actually works.
So when you later put this in the hands of developers and they develop something with an agile process, maybe building an MVP to start with, what features do they build first? Does that depend on what came out of it?
So what comes out of the residual analysis is a bunch of suggestions really around you should have this many components and these functions should live inside these components, and they should be organized in this way in order to give the right degree of redundancy and diversity and ability to survive and meet flexibility requirements. Depending on your development team, that might be a step too far. So some developers might throw this back at you and say, this is big design up front, we don't want to do this. In which case, if you've got that kind of developer in your team, you have to bring them into the process and let them be part of defining the architecture. There's absolutely nothing wrong with that. This isn't about a big bad architect making all the decisions. This can be done as a team. In fact, one of the things that you have to do to make sure that your random simulation is actually random is to make sure that there isn't just one person doing this. It needs to be an extended team. It needs to be people with different profiles and different backgrounds as well, from different aspects of the business network, and developers need to be there as well. And then which features will they build comes back to which features do we want to build first, what do we need to have, what's the TTM on these things, that kind of thing. It's better to have a whole system perspective while you're doing this. So even if you're just doing it for one part of the system for which you're responsible, which is absolutely fine, you still need to have input and ideas from the other people, because there's going to be X's out there that are going to hit you. And if you're blind, if you've put in a silo between you and different parts of the team, then you put a silo between you and your technology and their technology, and your understanding of the business network and their understanding of the business network. So if you're stuck in that kind of pattern, you need to have someone who can cross the line regularly. Um, no, and I've worked in many projects where there have been too many people and too many thoughts. It's a commonly occurring problem in our business. This I've actually used to calm those situations down in large organizations where you have strong-willed developers, and because of the organizational structure, because of history, you also have 12 architects on the team, and all you get is noise and conflict, and this helps people focus, helps them calm down, gives them something to aim at. It also means that if you're an architect with a very strong opinion and you come to a team and you say, we've got to do it like this, the team can say, show me your matrix, show me the stressors, how did you get to this, how do you know this is the right thing to do, and it opens up conversations in a completely different way.
If you want to do this with an existing architecture,
yep. Yes. Yeah, your residues are already set by someone else in an existing system. That doesn't mean, and you're going to make changes, so you can work to understand what impact am I going to have on the overall residue of the system, and make sure that it goes in the best possible direction, even if you must inherit those parts. With legacy systems, this can also be a good way to show why does this hurt and where does it hurt. Because it'll come out in the matrices, and you'll see these things are coupled together in this architecture, and these matrices are showing that it absolutely should not be, and that's why it's hurting. And so I do a lot of review, so people tend to bring me into their projects when the project has crashed. So the project's already there, the residues are already there, and I use these analysis tools, which essentially produce spreadsheets to show this is why it's crashing, and they tend to be all red and in the Excel sheet. And it's an excellent way to review an architecture as well, and to get an understanding of what's actually happening in this system. So I think we're out of time. So thank you for coming, thank you for listening. Good luck out there.